Yeah, camps on everyone. Let's start off. Let's see. Others to keep your camps on. Who else is missing? Okay. So this was the thing that we did last time. Next thing. What happens if you keep a resistor and a capacitor together? So before jumping into that, we will study something called steady state. You guys remember the steady state? We have done this before. Where do you hear this? Fluid mechanics, steady flow, streamline flow. Where else did you hear? Heat transfer, right, Puraja? Yeah, conduction, heat transfer in steady state. So what do you mean by steady state? If you guys remember, if the property at a given position does not change with time, the system is said to be in steady state. So for example, if you look at fluid mechanics, if you look at point A here and point B here, now if you see the pressure at A and B, so here the properties of pressure and velocity. Pressure and velocity of the liquid at that point. At a given position does not change with time. You're getting it? So it does not mean A and B ka pressure will be always equal. See, remember this example I gave you there? Let's say if our traffic is flowing and let's say here the speed limit is 30 kilometers per hour. Here the speed limit is 20 kilometers per hour. Here the speed limit is 10 kilometers per hour. If they actually follow the rules, so every vehicle that comes here will have a speed 30. The same vehicle, when it comes here, speed becomes 20. So doesn't matter whether a lorry comes here, car comes here, bus comes here, all will have speed 30. So velocity at a given position is constant. Are you getting it? But velocity changes with time. So this vehicle ka speed is changing with time. But that at a given position, every vehicle that comes there will have the same velocity. Is that making sense? That's what we call a steady state. Steady state doesn't mean everyone has become constant or everyone is equal. So same thing. So here PA pressure at A need not be equal to pressure at B. Need not be equal. They can be also, but there's no compulsory. So be careful when you hear the word steady state. It doesn't mean all are equal or uniform. And the same thing when we did in heat transfer. If you had a rod here, let's say this temperature was 100 and this temperature was 0. This was 80. 60, 40, and let's say 20. And the heat inflow is equal to heat outflow. So here the temperatures have become constant at a point. Temperature is not same everywhere, but at a given position, temperature remains constant. So no matter how long you wait and see, that 60 degrees will always remain 60 only. Now in current electricity, when we say, let's say if you have nodes like this, so each node, the potential remains constant. Charge on the capacitors remain constant. Current in the branches remain constant. So in circuits, we say the voltage at the nodes current in the branches obviously if the voltage is constant, then the current in the branches has to be constant. If the current is constant, then the charge on the capacitor also should not change, because if the charge on the capacitor changes, then the voltage will change. They do not change with time. There in circuits, whenever someone says, the circuit is in steady state, this is the meaning of it. The voltages won't change anywhere. Different branches can have different currents, but for a given branch, it will always remain constant. Is this clear, everyone? What is the meaning of a steady state? Clear? No. So therefore, in a capacitor, charge on a capacitor is constant. Therefore, current in the capacitor is 0. So if you take a capacitor, current is I and this is Q in steady state. I is equal to dq by dt, which is 0 since Q is constant. So in steady state, current and capacitor is 0. Now we have two cases here. At T0, when the circuit is, when the switch is just closed, a capacitor behaves like an wire. Meaning, see, I'll tell you the reason for this. Let's say if you have a capacitor and you connect it to a battery. Initially, it is empty 0, 0. The moment you close the switch, the first electron which comes from this plate will go and get accumulated on the other plate, isn't it? So for the first electron, is there any opposition? It just goes there. But when the second electron tries to go here, this electron which is already there will repel the second electron. That means as charge is accumulating on the capacitor, it becomes more and more difficult for charge to come and accumulate. So for the first electron, that is the first instant, there is no resistance. So if you take an empty capacitor and if you just close a switch, it just behaves like a wire. Again, it should be an empty capacitor. Offers no resistance initially. Once there is some charge on it, it will start giving an opposition. So whenever at T0, an empty capacitor can be replaced with a wire. At T infinity, if you keep the capacitor for a long time, it becomes full. If it becomes full, that means no more charge can come inside. If no more charge can come inside, that means there's no more current inside. So at infinity, a capacitor behaves like an open circuit. So has infinite resistance. There, this is the initial conditions and the infinity. So infinity is also the steady state basically. Meaning you left it for so long, the capacitor has become completely full and the system has reached a steady state. So this is the first thing. So first we'll study the circuits in a steady state and then we'll see what happens if you change the time. So let me give an example, but any doubt so far? And again, whatever you're learning today, exactly same stuff will again repeat in LR circuits. We have later on something called inductance and resistance karka. Every technique that you're learning, we'll use it again. Only difference, T0, it will become an open circuit, T infinite, it will become a wire. So it's just reverse of it. But every technique that you're learning today will be again coming up. So let me show an example how they'll frame a question on this. Let's say we have a circuit like this. There is a switch. This is V, this is R, this is R, this is 2R, and this is C. The switch is closed at T0. The question would be like this. Find current I at T0 and T tending to infinity. Means you just left the switch for a long time. Find charge on the capacitor at infinity. So let me show you one. So at T0, draw your circuit. At T0, what will happen? The capacitor will behave like a wire. This is how the circuit will look at T0. Always you have to draw a circuit. You can clearly see 2R and R are in parallel, 2R by 3, 2R by 3, R are in series, 5R by 3. So R equivalent will be 5R by 3. So current I will be 3V by 5R. This will be the current. The moment you close the switch, this is the current. The instant you close the thing. Now, if you leave this thing for a long time, now it becomes an open circuit, but always draw the capacitor because they're going to ask you for charge. So if you remove that, you won't be able to find that charge. So how do we draw this? So whatever current I flows here will flow through this resistor, will flow through this branch. So basically there'll be, and let this charge be Q. Basically there'll be no current in the branch connecting the capacitor. So I is 0. That's the meaning of steady state. Since the charge on the capacitor is constant, there can be no current on the capacitor in steady state. So this particular branch will have 0 current. So keep it in the circuit, but let it be there. Then if you see current is only flowing in this here, so you can clearly see I is equal to V by 2R. So whenever they ask you to find the charge on a capacitor, generally Kirchhoff's law. Apply Kirchhoff's loop law in this. I'm going to the capacitor, so minus IR, minus Q by C, and plus capital IR. Small I is 0, Q by C, and this is V by 2. So Q is equal to CV by 2. So that's your final charge on the capacitor. So at infinity, the capacitor ka final charge is CV by 2, and there is no current in that branch. Please have a look at the example. This is how you solve circuits at T0 and T infinity. What happens in the middle, we will see that later on. Mains may generally ask a lot of questions based on this, T0 and T infinity. Have a look at this page. Any doubts on this, ask me. So this circuit at T0 will look like this, at T infinity will look like this. The current has changed. Current used to be 3V by 5R, it has become V by 2R. Any doubts on the example? Yeah, go ahead. Now you guys try this. Find I at t0 and t infinity, and find the final charges on the capacitor. Final charges meaning infinity way. It doesn't matter how many capacitors you have, the story is still the same. If the capacitor is initially empty, it doesn't resist. After a long time, it will not let any current flow through it. I can have 100 capacitors, the story is still the same. Get this, you got 2 minutes. There we are. Draw your circuit, T0, T infinity. If you draw, you will see. T0, make it a wire. T infinity, keep it there, but current will be 0. Pi v by 2r, that could be right. Let's see. T0, this is how the circuit looks. All are in parallel. See, if this point is A, this is also A. If this is B, this is also B. You can clearly see all are in parallel. If all are in parallel, then the R equivalent will be how much? RR will be R by 2. R by 2 and 2R will be R by 2 into 2R by 5R by 2. 2R by 5. Current I will be V by 2R. Yes. At T infinity, finding the charges is a pretty good one. That is a difficult one. Most people can handle the current. The moment they ask charge, people struggle. So you need to understand it's draw the circuit, let the current be I. This current will be I. This will be I, and I again. So on the capacitors, there will be no current. So just draw the circuit. If you draw a circuit, you'll get the answer most of the time properly. Now, since we don't know the charges, I will take this guy as Q1 and this guy as Q2. Be careful, there's no guarantee charges are equal. Always take it as Q1, Q2. Now, if you can see the circuit here, the current all three are in series, so R equivalent will be 4R. I is equal to V by 4R. Apply Kirchhoff's law in this loop and in this loop. First, let's write the left loop. I'll start from here on the top. So that would be minus IR. I'm going from negative to positive plate. Plus Q1 by C minus IR is equal to 0. So Q1 will be 2 IR CV by 2. Then I'll take the right loop minus Q2 by 2C plus I into 2R. Again, I'm going here plus I into R is equal to 0. So Q2 will be, that will be 3V by 4, 3CV by 2. Check. Right, Poroja. Check out the charges. Charges are the most important ones. So draw your final circuit. Don't remove the capacitors. Keep them there. Say I is 0. Let the charge be Q1, Q2. Because when you use the loop law, you will need that thing. Most people, what they do, they just write like this. They'll keep it open like this. Current though, you'll get it. The moment you ask for charge, then you will not understand what to do. Some cases you can figure out, but circuit becomes complex. This will help. Is this clear, everyone? Any doubts on this? All clear? Let's see one more. Find the current at I, T0 and infinity and final charges. T0, how does it look? Draw the circuit. Always draw the circuit. I did a mistake. Wait. I understand why you're not getting it. Put one more resistor here. Now do it. You got infinity current in the beginning. That was infinity in the beginning. I forgot an R. I is not 0. At T0 current is infinity. Abhi V by R aayega. Yeah. Get the charges also. Finish it off. I'll give you a minute more. I was wondering why you guys are struggling. I realized it. Hmm. At T0, this is how your circuit looks. So whatever current that comes out of the battery will simply go from the top. The whole circuit got shorted actually. This guy and this guy are gone. I is V by R. At T infinity, whatever current comes here will go through the resistors. Current in these branches will be zero. Let this charge be Q1 and let this charge be Q2. So I can use this loop and I can use this loop. So I will be, there is one more resistor here. So V by 4R minus Q1 by C plus IR is equal to 0. Q1 is CV by 4 minus Q2 by 3C plus I into 2R is 0. Q2 will be 3CV by 2. Yeah, did I get it right or did I go up? Looks right. Check your steps, everyone. You want to find the charge, put it in a circuit, let it be Q1, get a loop and finish it off. Ah, yeah. Getting it, one of the safest way that I found. Matlab here, luckily you can still argue. Potential difference across this is potential difference across this is across this, and you'll get an answer. Actually, I could have kept a resistor in the middle also. The answer still won't change. Clear? Find final charges. I just dumped a bunch of resistors. I have no idea what is this. Let me also try. So I try. I'll give you a minute more. Draw the final circuit. Hmm. Let's see the circuit. So at infinity, right? I can remove this. This guy doesn't work. This guy doesn't work. These two are in parallel. If you actually observe, these two are also in parallel. So let's do one thing. Let's call this thing B. Let's call this thing A. A. This is A. This is C. This is C. This is also B. This is also B. Nay, these two are actually in series. This is in D. Let's read all the circuit. A, C, D, and B. These two are between A and C. This is between C and B. This is between B and D. This is also between B and D. And we have one between B and C हो गया. C and D भी हो गया. How many are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Who else is left? A and B. One is there. Actually, this guy is useless. This is gone, na? That is useless, isn't it? It is just hanging in air. Look at these two. These two are in series and they're connected to the same terminal here. There's no potential difference across these two are. Is that making sense? The circuit is just hanging in air. I'll show you see how. Let's put D outside here. This is B. This is D. You just took a resistor connected like this. Forget about D actually. Like this. And you connected it to B only. And you simply called this point D. That doesn't make sense, right? That is nothing there. Are you getting it? If you have a terminal, see. If I take a battery resistor here, resistor connected like this, what will happen? That's useless, isn't it? So this part is actually useless. This is what shorted. So basically this resistor and this resistor are also useless. Okay, so we got a circuit. In this grand scheme, where is your capacitor? It is between C and D. Since there is no current, D is also actually B only. So the capacitor is between these 2 points only. So B and D are same potential. There's no current. This I is 0. And this guy is C. Where is the other capacitor? This is between D and B. That is gone actually. That capacitor is connected to U only. Clear?
So
Now we can solve the circuit.
that first D that you have made, Won't that
Hmm.
also be C because there is no capacitor, right? We treat that as a
अरे
conducting magnet.
नहीं infinity रे God, infinity में capacitor behaves like what?
अच्छा अच्छा infinity.
ओपन सर्किट ना,
तो
ऐसा
you're
होगा,
talking
बीच
about
में
the
गैप था वो।
initial.
अरे
So the initial का तो ये नहीं रहा.
initial we are not taking ना, this is at
Okay.
infinity ना, question is final charges रे।
अच्छा अच्छा ठीक है.
Got it? And your battery is between these two. This looks like proper zombie, some kind of fish actually. ठीक है, I think you're done actually. What is this two? These two are in parallel, that is R by 2. This in series, 3R by 2, 3R by 2 and R. How much is that? 3R by 2 and R, 3R by 5. 3R by 2, yeah, 3R by 5. So current I will be 5E by 3R. So current I will go from here. This will split. How much will it split? This whole thing is 3R by 2 and this is R. So the current will split in the ratio of voltage is same in the opposite resistances. So it should split in the ratio of 2:3. So 2:3, that will be 2I by 5. This will be I by 5, I by 5, and this guy will be 3I by 5. You can check it out. This will be 2I by 5. So voltage across VC minus VB will be 2IR by 5. Therefore, the charge on the capacitor Q will be C into potential difference VC minus VB. So you can solve from there. You got it. So IR will be 5V by 3, 2V by 3. Bolo.
Sir, so like my logic is telling me that basically this AAC part we can convert into R by 2. So then basically current will come out from A and then it will flow to C and then it will flow to B. And then once it goes down, like we are ignoring that left side part anyways, we can cut it off. But then there's still
Right.
one resistor, right? So it should be in series, not parallel.
Yeah, what are you talking? This and parallel, they have same potential difference.
So
Oh
the
God.
last behind it, shouldn't it?
This whole thing and this thing are in parallel. Right? So, Bolo, what do you think?
So it's going like that, so it should.
This and parallel or not?
Yes, but sir,
So
battery
what is the
terminals not
problem?
connected at B, right?
Battery is connected at B only, na? Battery is what connected then between these two only, na?
But
Yours,
resistors between B and the battery, right?
there is one more resistor you're saying.
So between B and
Didn't I include that? I didn't include that. 2, 3, 4, 5, 6. I draw the circuit wrong. That resistor is here. Sahi bol rahe ho. You're right. My mistake it was. This you're saying, na?
yes, sir.
सही बोल रहा था. You're right. I goofed up. I didn't see that. I thought A and B are connected. अभी कितना आएगा equivalent? How much is this? R by 2, R, 3R by 2, 5R by 2. This is much better actually. 2V by 5R. That will be I only. इतना headache भी नहीं है. Life is easy. Then Q is equal to C into IR. 2CV by 5. Now fine. Anyone else found any other mistake? I'm obsessed about this cutting this part. I forgot that RA is. Anyways, it's a good one. There. If you understood this thing, I think your steady states are fine. All clear with this? Next thing. So we know how to find the circuit at t0 and t infinity, but what if you ask me at some time in the middle? So first, the standard one is RC charging circuit. Now listen to the process. The process is more important. At a mains level or a CET level, right, the results are important. But advanced they don't ask you the direct results as such. So if you have an empty capacitor with a resistor, let's say you have a battery with a switch, V, C, and R. So the moment you close the switch, you have some current here, and this will be charge Q here. Remember, this is a non-steady state. The current is not constant. The charge on the capacitor is not constant. They're changing continuously. This is a non-steady state. And this current I is dq by dt. So in a non-steady state, it doesn't matter what state it is, Kirchhoff's law is always valid. Apply Kirchhoff's law. V minus IR minus Q by C minus IR is equal to 0. CV minus Q by CV is equal to R into dq by dt. dq by CV minus Q is equal to dt by RC. Integrate this. I hope everyone remembers this integration. Integral dx by ax plus b is 1 by a ln ax plus b. If you have done integration, this is quite an easy one. If you have not done, do remember this. Limits will be 0 to t. Now be careful. Technically, it should be q initial, but here it is given 0. So that is important. So if the capacitor initially has charge, the limits will change. Everything else will remain same. This guy will be minus ln CV minus Q by CV minus 0 is equal to T by RC. So you will get Q is equal to CV into 1 e power minus T by RC. And the current I is equal to dq by dt. That would be V by R into e power minus T by RC. There, this is your standard RC circuit ka results for charging. Again, these are valid only if the capacitor is initially empty. More than the results, understand how I took the whole process. I said let the charge be Q, let the current be I, and then we did this. Yeah. Now, if you try to plot a graph, Q versus T graph and I versus T graph. So initially the charge was 0. And you can see the charge will take infinite time to reach a maximum value. Initially current was V by R, and this thing decays. Again, this also takes infinite time to become 0. Here we define something called a time constant RC. Again, nothing fancy here. You simply made, e power minus T by RC, and you put T is equal to RC, got e power minus 1. So you get a value 0.63 CV. That's it. The 63% really doesn't have a great significance because 1 by e ka value turns out like that. Similarly, tau here, this value comes out to be 0.37 V by R. So we define this time constant tau is the time taken for the capacitor to charge 63%. If you put an empty capacitor, it charges in 63% in one time constant. And you can also say current decays by 60%, 63%. The reason the 63 comes is because of 1 by E ka value. Clear with the integration? Next thing. Can I turn the page? RC discharging circuit. So if you have a capacitor already charged, plus Q and minus Q. So the moment you close the switch, let the current be I and let the charge be Q. So Q is the charge on the capacitor. I is equal to minus dq by dt because Q is decreasing. So if I apply Kirchhoff's law, you will get a minus IR minus Q by C is equal to 0. Q by RC and this is plus Q by C. I'm going from positive to negative plate. This will be minus dq by dt. Minus minus goes off, and this is Q by RC. dq by Q is equal to minus dt by RC. Initial charge was Q, small q, 0 to t. We end up with Q is equal to Q e power minus t by RC. So higher bar, the story is always the same. Let the charge be Q, apply Kirchhoff's law, and then finish it off with that. If you plot the graphs of Q versus time and I versus time, the graphs would kind of look same. This was Q and this was initially whatever is the value I. Same story here. In one time constant, the charge becomes 0.37 Q. In one time constant, the current becomes 0.37 I. These are the main results. Did you notice something? This result kind of looks like N is equal to N naught e power minus lambda t, radioactivity. It's a first order reaction. Look at this thing, dq by dt q power 1, na? This is the first order reaction. You know where else you have seen this? Anyone remember? A is equal to A naught e power minus bt by 2m, damped oscillations. Yeah, result. It's also first order reaction. So that means you can use all the concepts of half-life and everything here. Find the time when the capacitor charge in the capacitor becomes half. It's an half-life. What is half-life ka formula? Ln 2 by lambda, na? Lambda ka place mein you have 1 by RC. So RC ln 2 is the half-life. This is damped oscillations. This is your law of radioactivity. Max doesn't care. The equations look same. It's a first order reaction, chemical kinetics. Yeah. Next thing. There. So the main thing, you should know the process, charging and discharging. This is R, this is V, this is C. This is minus 2 CV and this is plus 2 CV. Find the time. When the charge on the left plate becomes CV by 2. This plate ka charge should become CV by 2. What is the time? Let's get this. So this is an RC charging circuit where initially there is a charge, meaning you can't use your formula. These formulas will not work. So be careful, don't blindly use them. And find the current when the charge on the capacitor is 0. There, let's help both of them. RC long 3/8. Okay. I'm not sure though. I don't know the answer. Draw the circuit. Like I said, the equations will look exactly same. The only thing that will change is the limit. So let this be current I, let this be charge Q. V minus IR minus Q by C is 0. CV minus Q is equal to R dQ by dt. dQ by CV minus Q is equal to dt by RC. Limits. Now this thing will change. Now be careful. You have taken the left plate as small q. What is the charge on the left plate initially? Minus 2 CV. So the limits will go from minus 2 CV to q. I hope you have taken minus 2 CV and not 2 CV. Be careful with that. And then you're done. So this will be minus ln CV minus q by 3 CV T by RC. This will be Q is equal to CV 1 minus 3 e power minus T by RC. What this? This will be the charges function of time t. You can verify if you put t0, I will get minus 2 CV, and if you put t infinity, I'll get CV. Looks right. Check this thing. Most people goof up the limits. They take plus 2 CV there. Generally, people do that. So if you're not done, then good. You're done. What do you want to find now? You want to find when the time is CV by 2. So put Q is equal to CV by 2. This is CV 1e 3 times e power minus t by RC. Solve this, you'll get the time from here. I'll leave it to you. Then what is the next question you want? Find the current when the charge is 0. So put Q is equal to 0 CV 1 e power minus 3t by RC. So from here, you'll find the time again here. Let's call it T2. And the current I will be dq by dt, which is CV 3 e power minus t by RC by RC. 3v by r e power minus t by RC. So you want current when Q is 0, then the current I will be, substitute T2 there. That should give you the answer. Clear with that? I'm not simplifying, but check it out. Got the equations right. Any step you're not convinced or anything else that you see that you're not convinced, please ask. So main thing is that once you got small q ka value, I can get whatever I want. I can find time when q is CV by 2. I can find time when q is 0. Once I know the times, I can differentiate the charge. I'll get the current, put it there, and you're done. Is that clear, everyone? Any doubts on this? I can even ask you one more question. Find time when power in the capacitor is maximum. That is maximum rate of charging. Or discharging, whatever. So the capacitor energy rate is not discharging or not getting, filled up at a constant rate. How will you do that? RC lon 6 क्या first वाला? How will you find the power? I know it still didn't teach you, but you know the power ka formula, right? V into I. It's not I square R. This is not a resistor. Power ka formula is always V into I. In case of a resistance, V becomes IR. Think for a minute. It's a good one. They can pop up like that. Yeah, you can differentiate Q function, but that will give you I, right? What is V? V is not voltage of the battery. See, for the C part, power is nothing but V into I So exactly what is V? V is the voltage. So if you want power in a capacitor, this is the voltage across capacitor into current in the capacitor. It should be across the element. So voltage across the capacitor is Q by C. Current is I. So Q by C is this guy, which is V into 1 e power minus 3t by 3 e power minus t by RC. And current will be this guy, which is 3V by R e power minus t by RC. So there, so we get 3V square by R e power minus t by RC minus 3 e power minus 2t by RC. This is your power as function of time t. Now you need to maximize this. Maximum minimum dp by dt is equal to 0. Isn't it? The question is at what time the power is maximum. So if you do this, you will get how much? This guy is gone anyway, so that will be minus 1 by RC e power minus t by RC plus 3, that will become 6 actually, 6 by RC e power minus 2t by RC is equal to 0. The RC goes off. You're left with 1 by RC. I'm getting again RC ln 6. Yeah. So when the charge is C by 2, that is when it is maximum. Interesting. But got the process how to do? Forget about the numbers. You can check your calculations later on. Process is clear. When you say power is VI, don't take voltage of the battery. If you take voltage of the battery, that will give the power from the battery. Na? The question is not power in the battery. Power in the battery will be maximum and current is maximum. The problem with the capacitor, the voltage is messed up, current is also messed up, so the product has to be maximum. Any doubts on this? There, you can play like this. Question would be of that sort. Any doubts?
In B part.
हाँ B part you can find with Kirchhoff's law. सही बोल रहा है. इतना करने का जरूरत नहीं था. You could have simply said V minus Q by C minus IR is 0. That would have been faster. Yeah, you're right. Take a break. Come back in 5 minutes. Take a small 5-minute break. Any doubt so far? Come back by 9:40. So we have two RC charging circuits, and someone has given a graph like this. So the batteries are V and 2V, resistance R1, R2, C1, C2. When you plot I versus T graphs, this is a I1 ka graph. This is I2 ka graph. So both the graphs start from the same point. So using this data, compare C1, C2, R1, R2. Greater, equal, less, whatever. Get that. This will be a pretty good mains question. Okay. They're not equal, right? Arush might be right. Let's see. So first thing, when you notice the graph, both have the same initial current. So for RC discharging circuit, if you see the initial current, it is, yeah, both are empty, so it is V by R. So this is V by R1. This is V by 2V by R2. And they have same initial current. At T0, the capacitor behaves like a wire. So R2 by R1 is 2. R2 is greater than R1. Then, if you notice this, when the value becomes 0.37i, remember this? When the current decays by 63%, it should be a time constant. That means this is the time constant for I2 and this is the time constant for I1. So time constant of the first circuit is greater than time constant of the second circuit. That is R1, C1 must be greater than R2, C2. But we already know C2, R2 is nothing but 2R1. So C1 is greater than 2C2. If C1 is greater than C2, then yeah, C1 is definitely greater than C2. Clear with that? C1 by C2 is greater than 2. So that means it is greater than 1 also. So C1 is greater than C2. Check your answers. Easy? So there, you get it from the initial condition and then you get it from the time constant. Any doubts on this? Next one. Next one. What if you have two capacitors? This is C, this is 2C, minus 2CV, plus 2CV. This is 3CV and minus 3CV. I want you to find the charge on this green plate. At time t. There, none of the formulas will work. You always have to go back to the derivation. Do you remember how to do when you have two capacitors? Let one of them have charge Q. So charge conservation. So try. I'll give you 2 minutes. As long as you get the equation, the max part is the easiest one. Let me show you the circuit equation if you got that. So remember the green plate is the one you want to find. So generally, whenever they ask you to find the charge on a particular plate, keep your life simple. Let that be Q. So let this charge be Q. right? Now, if this is Q, remember these two plates combined, what's the total charge? 5 CV. So that charge has constant, right? That charge cannot go anywhere, isn't it? The total charge on the two central plates is constant, 5 CV. That means on this guy, the charge must be 5 CV minus Q. The total charge on those two plates must be constant no matter what you do. Put a resistor, put a battery, I don't care. Those two has to be constant. Because both the plates are in air, they're not touching anyone, isolated. So let the current be I, let the current be I, let the current be I. There you got your equation. Apply Kirchhoff's law, you're going from negative to positive plate minus Q by C, then you're going from plus actually. Then 5 CV minus Q by 2C, then you're going through resistor minus IR is 0. There. Can you solve? I'll give you a minute. Done. Physics part is over. I is dq by dt. What will be the limits? Remember, initially the charge was 2 CV. Don't put 0. Initially the charge on that plate was 2 CV. So small q ka limits will be 2 CV to small q. Every question you're doing, similar one you will encounter in inductors. PQ by 2C minus 5V by 2 is equal to IR. This is right. Got the same? Check. Got it? I skipped a lot of steps, so check it out. There, this is how you find for two capacitors. So the main thing is once you got the equation, see the main thing is the circuit. Always draw a circuit. Don't imagine like somehow you can see it in air and figure it out. Nahi hota hai. It is just your illusion. Until unless you have some super photograph memory. Ah, Devansh. Where is this guy? He raised his hand, he got disconnected. He came back. Ah, Devansh. बोलो.
सर 5 प्लस होगा कि 5 माइनस?
कहाँ पे बोल रहे हो? ये?
हाँ हाँ
ये -5 से उससे जाएगा ना तो प्लस होगा ना?
5 नहीं 5 प्लस 3e होगा.
Yeah, this minus sign when it goes in multiples, it will be still -3 CV only, ना?
सर बट t को 0 डालेंगे तो फिर 4 cv/3 आएगा ना.
t को 0 डालेंगे शायद you got disconnected.
Then we need 3 into 2 CV, no?
Where
Denominator में, in the integration of dq
denominator में
will be 3q, मतलब 3 into 2 CV, मतलब 6 CV minus 5 CV. Then you do CV.
I did a mistake there. That is 3 2 ना 3 था मैंने 3 मल्टीप्लाई नहीं किया CV था ये.
फिर अभी +1 आएगा वो.
या मैंने वो 3 मल्टीप्लाई नहीं किया. सही बोल रहे हो. Clear? Got the steps, no? Check it out. Next one. So let's say we have a circuit like this. This is R3, R2, R1, V capacitance. This is A, this is B, the switch is like this. So initially switch is connected to A for long time. Then what you did, the switch is flipped between A and B for a time interval of T. Flipped to B for time T, then to A for time T, and so on. You do this infinite times. Plot Q versus time graph. Approximately plot the graph for charge versus time. So if you're flipping the switch continuously, see when you connect to B, what will happen? You will discharge. When you connect to A, what will happen? You will charge. So the capacitor is charging and discharging continuously. So let's say you keep the switch at B for 1 second, then bring it back to A for 1 second, then B to 1 second. You're doing this continuously. How will the graph look like? Any idea how it will look? Show you. I'll ask you one thing, see. Tell me one thing, how long, forget about this thing. If you take a capacitor, how long will it take for it to discharge completely? Infinite time. Similarly, if you take an empty capacitor, or even if you have a capacitor with some charge, and if you charge it, how long will it take to completely charge? Infinity. Now how will the graph look like? Means you can never fully discharge, you can never fully charge back. So if you look at the circuit, so when it switches flip to B, you're discharging. When you flip to A, you're charging. So initially it is already at A. Now so this was the initial charge, whatever is that, CV. So time T. So technically, see, the graph should look like this, isn't it? So you can't have a full graph, you'll have a part of it. So you'll have something like this. So this is for the first time T, when you are at B. Now what will happen? Now you connected it to B. Now technically, if you just leave it like this, how long will it take to reach the initial value? Infinity. You can't have a full graph, it will be somewhere cut off here, isn't it? So your graph will stop here. Now again, if you discharge it, technically it should go to infinity. Again, it will take a long time. But again, that won't be there. It will cut off somewhere here. So this graph will keep coming down. This graph will keep pushing it, but it can't go to the initial value again. You're getting it? This will just keep coming down. Is that clear, everyone? Because in the same time interval, you will always decay 63% of your initial value, isn't it? If you're decaying 60% initial value, the initial charge is just going on down and down and down. So when you're trying to charge also, you'll get the 63% charge. So it doesn't work out. Think of like this. Let's say you have 100 rupees. Okay? Just simple example thing. Let's say if you lose 50% and then if you gain 50%, how much money do you have? You have 100 rupees, you lost 50%, and then you gained 50%. How much money do you have? When you lost 50%, you got 50. 50 ka 50% is 25 rupees. You got 75 rupees back. You don't reach 100 again. Clear with that? Percentages will look same, but they're quite deceiving. So, is this clear? It will be a good main level question. They can still play more with this, but yeah, let's see one more. This is all great. So, advance me how they'll ask you. This is the example, first question that we did. Find the charge on the capacitor at time t. Let's get this. Right, I'll give 3-4 minutes. I'll give 2 minutes, then I'll show you the circuit. And I'll give another minute for solving. Let's see whether you got the circuit right. So let the battery give current I. Let this be small I. Let this be I minus I. So current will split like this. And this is charge Q. So the question is, what is dq by dt? Is it capital I? What is Q, small q? Small q is a charge on the capacitor. So if you differentiate this, that should give you current in the capacitor. Got it. So small I is dq by dt, not capital I. Then you write a Kirchhoff's law in this loop and Kirchhoff's law in this loop and eliminate capital I and get small I in terms of Q and then integrate. Try. If you have got till here, I think you're done. Current won't split equally. There is a capacitor sitting there. You can't say it will divide in the ratio of 1:2. No, that way. Be careful that R and 2R are not in parallel, people. There's a capacitor sitting in the middle. Initially capacitor is empty. Yeah, nothing is mentioned. Take that. Ohm, देखो ना, if you put T0, 0 आना चाहिए initially. Initially capacitor was empty. And time constant is also messed up. That is wrong anyways. Check your equations. V minus IR minus I into R is 0. I into R will be V plus IR by 2. That's your equation 1. Minus I into 2R minus Q by C plus I minus I into R is 0. This is minus 3 IR minus Q by C plus IR. V plus IR by 2. Minus 5R by 2. This will be Q by C minus V by 2. This is 2Q minus CV by 5RC with a minus. This is dQ by CV minus 2Q by dt by 5RC. Integrate this. 0 to T and 0 to Q. That would be minus half ln CV minus 2Q by CV T by 5RC. So small q will be CV by 2, 1 minus e power minus 2t 5RC. That's how you get this. You don't need capital I, you need small I. If they ask you for capital I, you'll get it. You know small I from here, you can substitute and get it. But there's a much better way to do this problem. There's an alternate, let me show you that. But have a look at this. You need to know this stuff. Even though we have a shorter way, if something changes in the question, this will always work. Could be lengthy. But like I said, once you got this equation and you got this equation, physics is over. The rest looks very big and tough and dangerous, but that's actually an innocent one. You just had a brute force integration. Clear? Any doubts on the steps, integration, anything you're not clear? So how do we do these kind of problems in a much faster way? Now, one thing if you observe till now, every question ka solution that we are getting, it has a general form. So we have a general solution for these problems. Which is Q is equal to A plus B into e power minus T by RC. Tau, e power minus T by tau. So here A and B are constants. Tau is your time constant. One second. So this thing, so that this is your general solution. Q is equal to A plus B e power minus T by tau. Normally, right, it is easy to use this for a single capacitor, but I think you can use it also for two capacitors. I'll show you a few cases. Let's see how that works. So, but this is your general solution. So step one, finding time constant. So look at this equation. If I can find A ka value, B ka value, tau ka value, my job is done, isn't it? Step one, finding time constant. So what we do here, if there are a lot of batteries, replace all the batteries with wires. Then find R equivalent across the capacitance. Then find time constant is equal to R equivalent into C. So I will just take the example, with the same question which we have done. So since we already know the answer, R, 2R, and C. So step one, make all the batteries into wire. So wire, resistor, 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 there. So you're supposed to find across the capacitor. So take the capacitor terminals as this. So this is 2R, R, and R. R and R are in parallel, R by 2, R by 2 this thing. So R equivalent is 5R by 2. Therefore, tau is equal to 5RC by 2. Same thing we got, see, 5RC by 2. You can actually even do it for these guys also. When we took the two capacitors, C and 2C, so here I can just make that C 2C into one capacitor, which is 2C by 3. Here the time constant is 2RC by 3. Can you see the time constant here, 2RC by 3? So even if you have initial charges, you can just empty them and finish it off. Because see, the time constant doesn't care what is your initial charges, isn't it? Time constant simply says the time taken to 63% decay. Whatever you had initial charge, I'll decay by 63% for an RC circuit. It kind of works. So this is the first thing, finding time constant. I know how to get tau. Second thing, step two. At t is equal to 0, your charge q is equal to q initial. This will be given in the question. So this q will be a plus b into e power 0, which is a plus b. Step 3 at t infinity, we know q will be q final, the steady state, which is a plus b into e power minus infinity. E power infinity is 0, I'll get a value. Now taking the previous question, this was V, R, 2R. We have done this. This is the first problem that we did. This example. This is the example we did, isn't it? We got CV by 2. You're done. So therefore, initially what you got? So in our question, Q initial was 0, which was A plus B. Q final was CV by 2, which was A. Therefore, B is also minus CV by 2. Therefore, Q is equal to A plus B, that is CV by 2, 1 e power minus tau is 2t by 5 RC. Same answer. You skip the whole integration. Step 1, finding the time constant. That itself is a mains level question. They'll give you a circuit and ask you to find time constant. Step 2, initial charge, that will be given. Step 3, steady state, we have to find the charge, which you have know how to do it. Once you know these three things, substitute in A plus B e power minus t by tau, and you're done. You can do the same thing even for capacitors also. If you have two capacitors like this, finally, forget about the resistor. Can't you find the final charges? Both the capacitors will have same potential, isn't it? Current becomes 0. Then do you guys remember that formula which I taught you? Capacitors mein. If two capacitors of same polarity is connected, you can use C1 V1 plus C2 V2 by C1 plus C2. Don't remember. People are looking suspiciously. If two capacitors same polarity are connected, you can use C1 V1 plus C2 V2 by C1 plus C2. You can use that. You'll get the final charges, final potential. From there, you can get the final charges. So I can substitute here. Clear the steps. Let me give you one question and you also give it a try. This method is quite useful, saves you a lot of time from integration and all that steps. If it is a more than one choice question, this will really help. They can ask you time constant, final charge, and all that stuff. So using this method, let's try to solve. V, 2V, C, R, 2R, 3R. This capacitor already has a charge 2CV and this is minus 2CV. This is the switch closed at T0. Find the charge on the red plate as function of time t. There, if you got this, I think you know how to use this general result. And same thing again, we'll use in electromagnetic induction again. Like I said, every technique that I taught you, we'll repeat. Try this, I'll give 3 minutes. Step 1, replace all the batteries with wire, find R equivalent across the capacitor. Step 2, initial charge given. Step 3, find the final charge on the capacitor. Then put it in A plus B power minus T by tau and you're done. Let's see. First thing, R equivalent. So replace all the batteries with wires. This is how it looks, the plain circuit. R, 2R, 3R. You find the R equivalent across this guy. R and 3R are in parallel. That will be 3R by 4, 3R by 4 plus 2R. So R equivalent is 11R by 4. Time constant will be 11 RC by 4. Got that? Next thing, at T0, the charge Q was 2 CV. This is given data, which is A plus B e power 0. So A plus B is 2 CV. Now at T infinity, your circuit will look like this. You have to draw the circuit. The capacitor will be full. There'll be no current in this, but there's a charge. So all the current will flow through this, where I is nothing but V by 4R. So you want on this plate, so let this be Q and apply Kirchhoff's law in this, and this current is 0. This is minus I into 3R. You are going from positive to negative plate, minus Q by C plus small I into 2R, but small I is anyway 0. So this guy is gone. Hey, there's a battery also, I forgot. You are also going through a battery, so plus 2V is equal to 0. So I into 3R, that will be 3V by 4 plus 2V. 3V by 4, 4 to 8 minus 5V by 4. Q is equal to 5CV by 4. That's your final charge. Got this. And this is nothing but A plus B into e power minus infinity. So A is 5CV by 4. There you got everything. Now substitute the values there. So Q is equal to A plus B into e power minus t by tau. If A is CV by 4, then B will be 3CV by 4. So take out CV by 4 common, you'll get 5 plus 3 e power minus 4t by 11 RC. Got that? Steps clear, everyone. There is no need to integrate, nothing, you'll get the answer. Any confusion? There are 3 steps: time constant, initial value, final value. For final value, what you do? Capacitor, there will be no current. You know how to do steady state circuits. Any doubts on this? Clear? Then that is about RC circuits, getting it. So steady state and a non-steady state, and an alternative method in case you want to skip integration. I would prefer to use this integration. There is always a chance you'll go for one sign or somewhere here, but this is kind of safe. So definitely make sure to go through all this stuff, what we did last 5-6 problems here. Same things will again repeat in EMI, and these things do come in advance a lot. Mains may they might stick to only steady state, but advanced may they will expect you to integrate, and you should be quite comfortable with it. The next thing is non-ideal batteries. So till now we have been dealing with ideal batteries. And remember what a battery does? It maintains a potential difference. That's it. That is the only thing a battery does. But in real life, if you look at a battery, they do have some internal resistance. Due to the materials used in construction, there is an internal resistance. So every battery will have some resistance of its own. So whenever you're drawing an ideal battery, non-ideal battery, this is how you draw it. So this is I, this is R. This will be the terminals of the battery. There, this is how this whole thing is a battery. You cannot separate that R from the circuit. That R is always part of the battery. So this E is called EMF. R is your internal resistance. Now here, the current I is coming out of the battery. So here VA minus VB is your potential difference. This will be E minus IR. So be careful. Potential difference need not be same as EMF. I'll show you an example. So on a battery, when you see it is 2 volts, it doesn't actually give 2 volts. This is the potential difference. Suppose if the current I is going into the battery, VA minus VB will be E plus IR. So this is what happens when you're charging your cell phone. You apply a voltage greater than the battery. This is what happens when you're discharging a battery. So there was a theoretical question like this. Can the potential difference across a battery be greater than the EMF? Yes, it can be. So in this case, VA minus VB is greater than EMF. When you're charging a battery, the EMF has to be greater. So be careful whether the current is going in or going out, the potential difference will change. So potential difference becomes equal to EMF when current is 0. That means when you don't use the battery, you actually get the proper voltage. But if you're not using the battery, what is the use of getting a proper voltage? That is the unfortunate thing. You want the right value, don't use it. If you're not going to use it, why do you need a battery? Have a look at this. So let me show you an example. All clear with this page? Let's say you have a battery 2 volt, which has an internal resistance 1 ohm. You take this and connect this to a 3 ohm resistor. So this whole package here is your battery. And this is your potential difference. So now see, this internal resistance will behave like a regular resistance. It will be in series, parallel, it will do all that stuff. So here, if you see the current, it will be 2 by 4, it will be 0.5 ampere. Now, if I ask you for the potential difference across the battery, this will be 2 minus E minus IR. This will be 2 minus half into 1, which is actually 1.5 volt. There, this is the issue there. Even though the battery shows 2 volts, it is only giving 1.4 volt, 5 volt. So it actually depends on how much current you're pulling from the battery. The more current you pull, the less potential you get. That means the current depends on the external circuit. So depending on what kind of circuit you're connecting, you get different potentials there. So the ideal battery which we had, which didn't care about the external circuit, in real life, the battery actually cares about the external circuit. Depending on what you're connecting, your potential gets messed up. You pull too much current from the battery, it actually doesn't give the voltage you want. Example, you must have seen this. Ever seen this when you start the car, the lights of the car will actually dim for a moment and then come back to normal? Ever seen that happening? When you start your car, the lights are on, and when you start, when you switch on that engine, right, the lights will dim for a moment and come back to the normal. Nowadays, in the houses, we all have LEDs, right? But if you had bulbs in the house, this used to happen when I was in school time. In our kitchen, we used to have bulbs and we have a refrigerator. This refrigerator, right, once in half an hour or 20 minutes, the compressor switches on automatically. It's an old type. So, and whenever the compressor gets on, it pulls current from the circuit, means it needs current for some time to start. The whole bulbs in the kitchen, right, used to dim. Used to be back to normal in a second. Did you ever notice that? When you switch on your AC or a refrigerator, anything that takes a lot of current will actually bring down the whole voltage and the lights become dim. You don't see this in LEDs, but bulbs, you will see this. Best example is your car. You should definitely next time check it out. When you switch on your car, the headlights which are there, they dim and they come back to normal. So what's happening there? So if you have a battery, and let's say this is your bulb, and let's say we have one more device here, could be anything, AC or car engine, anything, R2 and R1. So initially this guy is giving current I that is going through the bulb. Now when you switch it on the engine, when the switch is closed, if you keep two resistors in parallel, what will happen? The overall resistance will decrease. If the overall resistance decreases, the current in the circuit will increase. Now this battery will give current I1 plus I2. The overall current from the battery bumps up. If the current increases, then the potential difference drops. This is the reason. So when you're switching on your car, to start the car engine, right, it needs a large current for a small time. It actually used to create a spark. We will see how to create a spark in EMI. So the potential difference, because the bulb is in parallel to the battery, the overall potential drops. The bulbs dim for a moment. So this is what happens in your house also. All the circuits in your house, right, are in parallel. So if one part of the circuit or one element starts taking a large current, the potential will drop in your house. The bulbs will become dim. Clear with this? And if you take this, potential difference VA minus VB is equal to E minus IR. I can modify this a bit. Delta V is equal to minus R into I plus C. This looks like Y is equal to MX plus C. So if you actually plot a graph between delta V versus I, it's a straight line where when current is 0, E becomes EMF, and when this becomes, this is EMF by R. Small r is the resistance. So there was a question like this in JE once. They gave a graph of the potential difference across the battery versus current. This was 2 ampere and this is 10 volt. And just look at here, when it is 10 volt, here at this point the current is 0. At this point the potential difference is 0. How can you get a current 0? You can get a current 0 if you don't connect anything in the circuit. Open circuit, there's no current. So in this case, delta V will be equal to EMF. I is 0. So EMF is 10 volt. Delta V 0 means what? The potential difference became 0. That means you connected A and B together. You shorted the circuit. In this case, I is equal to E by R, which is 2 ampere. R is 5 ohms. Are you getting the meaning of that graph? If you don't use the circuit, then EMF will be equal to potential difference. If you just short the circuit, that means if there's no resistor, you just short the battery, you get a maximum current. You get a maximum current, but there's no potential difference. And again, be careful. People say like this, sir, but if there is no potential difference, why is there a current? Did I say there is no potential difference across the resistor? I said there is no potential difference across the battery. There is no potential difference across the battery. There is a potential difference across the resistor. Be careful. V is equal to IR is used for resistor, not for the battery. Clear with this? That's a little intro about the non-ideal battery. So next class when we catch up, we'll continue from here. We will see combination of batteries. What happens if we keep these non-ideal batteries in series and parallel, a mixed combination? What kind of heat do they produce? We will see all that stuff. And then if time permits, maybe we'll start off with a little intro on ammeter and voltmeter devices also. Okay, with that we'll wrap up for the day. So do make sure to go through all this thing, especially whatever we did today, do try to solve them. Okay, with that we'll wrap up for the day. So any doubts, anything you can stay back and ask, or else you're free to leave. So take care, stay safe. I'll see you on again Friday, same time.